Good morning, everyone. I'm Chen from Huazhong University of Science and Technology. It's my pleasure to present our work titled DShuffle DPU-Optimized Shuffle Framework for Large-Scale Data Processing, which is a joint work with Huawei Cloud. Let's begin with the background and motivation. Data shuffle is a critical operation in distributed data processing systems such as Spark and Hadoop. It is responsible for exchanging intermediate data between stages to enable distributed computation. As a data-intensive operation, shuffle involves a large amount of disk I/O, network communication, and serialization computation, and it consumes a lot of CPU and I/O resources. Thus, it often becomes a major performance bottleneck for the entire analytic job. Today, with the rapid improvement of storage and network bandwidth, the CPU overhead of data shuffle becomes increasingly noticeable. To illustrate this, we conducted an experiment using the high-bench sort workload on Spark. The Spark cluster consisted of two nodes, each with a 16-core CPU, 32 GB of memory, an NVMe SSD, and connected via a 100 gigabits high-speed network. We also monitored the CPU, network, and disk utilization during the execution. As shown in the figure, during the shuffle phase, about 30 CPU cores were actively used, nearly hitting the physical limit of the machine. In contrast, both network and disk bandwidth were significantly underutilized, reaching only 25% and 51% respectively. This result clearly demonstrates that data shuffle introduced considerable CPU overhead, which can become a major bottleneck under modern storage and network environment. To further understand the source of the CPU overhead, we used the perf tool to profile the CPU time breakdown of the Spark job. The results show that a significant portion of CPU time was spent on data serialization and garbage collection. This issue becomes particularly prominent for workloads that produce a large volume of intermediate data. For these workloads, data serialization is required before node exchange and persisting per intermediate data. This process involves intensive memory access and data copies, resulting in significant CPU overhead. Meanwhile, the shuffle operation generates a large number of temporary small objects, which exacerbates the JVM's garbage collection pressure and further increase the CPU burden. Nowadays, DPUs are increasingly being used to offload storage and networking tasks from CPU. Today, major chip vendors such as NVIDIA, Intel are actively developing their own DPU products, and large-scale cloud service providers such as AWS, Microsoft Azure have widely deployed DPU hardware in their infrastructure. Given the close integration with the data path, we believe DPUs present a promising opportunity to accelerate shuffle operations. In fact, DPU hardware is well suited for offloading shuffle operations. First, the RDMA NICs and the PCI switches on DPUs provide high network and I/O bandwidth, enabling efficient data exchange across devices and nodes. Second, DPUs offer strong programmability, and their general-purpose cores can be used to offload the computation of shuffle operators. However, offloading shuffle tasks to DPU also presents certain challenges. Due to the limited frequency and the number of general-purpose cores on DPUs, a straightforward migration of shuffle operations may degrade overall task performance. The figure in the left shows the execution results of naive offloading shuffle operations to DPU. As can be seen, the task execution time increases by 1.5 to 1.7 times after offloading. To address the above issue, the existing approach, such as Smart Shuffle, dynamically distributes shuffle tasks between the host CPU and the DPU to overcome the computational bottleneck. While this strategy avoids performance degradation, it still consumes a significant amount of host CPU resources. Moreover, Smart Shuffle continues to rely on the host CPU for persisting intermediate data and performing data serialization, which introduce additional data copies and computation overhead. This highlights the need for more efficient offloading strategies. In fact, with the evaluation of DPU products, modern DPUs are capable of fully offloading shuffle operations without sacrificing performance. Firstly, modern DPUs are equipped with programmable data path accelerators that feature a large number of hardware threads capable of concurrent memory access. For example, the DPA on Bloomfield 3 DPU can provide up to 40 gigabytes per second memory access bandwidth. These hardware threads can also execute arbitrary computation logic, such as Fermat transformation, making them particularly well suited for offloading serialization operations. Second, the frequency and number of general-purpose cores on modern DPUs are steadily increasing. For example, Bloomfield 2 features only 8 ARM cores running at 2.4 GHz, while Bloomfield 3 offers 16 ARM cores at 3.0 GHz. This growing computational power provides strong support for full offloading shuffle operations. Additionally, modern DPUs feature PCIe P2P capabilities, allowing them to exchange data directly with storage devices without CPU involvement. These capabilities form the foundation for our proposed fully offload shuffle framework. Next, I will introduce the design of our shuffle offload framework. Our shuffle offloading framework is called DShuffle, which consists of 4 main components. The first component is a shuffle agent, which is responsible for interacting with Spark executors on the host, retrieving the output of map tasks and triggering shuffle operations on the DPU. The second component is a DPA-based serializer, which serializes the results produced by map tasks and passes them to the shuffle workers on the DPU. The third component is a shuffle worker pool, which executes specific shuffle operators such as aggregation, sorting, as well as handling network and disk I/O operations. The fourth component is the shuffle scheduler, which monitors the status of DPUs and schedules shuffle tasks accordingly. In DShuffle, all shuffle operations are carried out by the DPU, while the host is only responsible for notifying the DPU to execute the shuffle tasks. As a result, DShuffle can fully eliminate the shuffle-related CPU overhead on the host. To ensure efficient execution of shuffle operations on DPU and eliminate the computational bottlenecks, DShuffle introduced 3 key techniques. The first technique is DPA accelerated serialization, which uses multiple DPA hardware threads to accelerate the serialization process. The second technique is DPU direct spuling, which leverages DPU to direct spill generated intermediate data to storage devices without CPU involvement. Third is the fine-grained pipeline shuffle. The DShuffle integrates different hardware components to execute the shuffle operations. I will explain each of these techniques in more detail. First, I will explain the DPA accelerated serialization. The DPA is a set of programmable hardware threads on the DPU that can access host memory concurrently while not store instructions. This provides an opportunity to offload serialization tasks. In DShuffle, we first register metadata such as JVM object types and serialization context with DPA. During serialization, the host-side worker triggers multiple DPA threads to concurrently serialize different JVM objects from host memory and copy them into the DPU's ARM accessible memory. With this approach, the host is only responsible for registering metadata and initiating the DPA threads, while most of the serialization logic is executed directly on the DPA. As a result, the host CPU overhead is significantly reduced. Moreover, thanks to the parallel execution of the serialization task, the overall serialization performance is also improved. The second technique is DPU direct scaling. After serialization, the shuffle worker on the DPU executes operators such as sorting and aggregation on the data. These operations generate a large volume of intermediate data, which needs to be temporarily stored on disk for later processing. In traditional approaches, this build-to-disk process is handled by the host CPU, which introduces extra data copies and CPU overhead. To eliminate these costs, DShuffle enables the DPU to directly write intermediate data to disk while PCIe P2P transfer. Specifically, DShuffle first registers a set of temporal files on the host. The host pre-allocates space for these files and sends their metadata to the DPU. When intermediate data needed to be spilled, the DPU writes this data directly to disk based on the provided file metadata, completely bypassing the host CPU. To ensure consistency between CPU and DPU, the files are mounted as read-only mode on the host. This design avoids unnecessary data movement and reduced garbage collection overhead on the host, contributing to both performance improvement and CPU load reduction. The third key technique is fine-grained pipeline parallelism. Compared to traditional approaches, DShuffle adopts a fine-grained and deeper pipeline to organize the shuffle process. As shown in the figure, in conventional offloading designs, a single shuffle worker on the DPU is responsible for all tasks, including serialization, operator execution, and the intermediate data transfer. In contrast, DShuffle decomposes these tasks and assigns them to specialized workers. DPA workers handle serialization, shuffle workers perform operator execution, while spill workers manage intermediate data spilling. By organizing these workers in a pipeline fashion, DShuffle exploits the parallelism of different hardware components on the DPU and significantly improves the efficiency of shuffle execution. Let's come to the evaluation. Our testbed consists of 2 compute nodes and 1 driver node. The configuration of each compute node is shown in the table. Each compute node is equipped with an Intel CPU, a Bloomfield 3 DPU, and a 2 TB NVMe SSD. The 2 compute nodes are connected via a 100 gigabit switch. We mainly use 4 high-bench workloads for evaluation: sort, ternary sort, repartition, and word count. The first 2 are shuffle-intensive workloads that generate a large amount of intermediate data, while the later 2 are compute-intensive workloads. We compare the following approaches. The first approach is native Spark, the unmodified baseline implementation. The second approach is a naive offload scheme, similar to Smart Shuffle, where shuffle computation and network transfer are offloaded to the DPU, but serialization and the intermediate data spilling are still handled by the host CPU. The third is our proposed DShuffle, which fully offload all shuffle operations to the DPU. We first show the performance improvement of DShuffle. For the shuffle-heavy workloads, DShuffle delivers performance improvements with speed up ranging from 50% to 33%. This is primarily due to the near elimination of network and disk I/O overhead, as well as substantial reduction in serialization and garbage collection costs. For compute-intensive workloads, DShuffle is able to maintain performance without degradation. Next, we evaluate resource utilization. The DShuffle system effectively reduced host CPU usage, saving about 8 CPU cores during the mop phase. In reduced phase, CPU consumption related to the garbage collection is significantly reduced by about 20%. In contrast, The naive offload approach suffers from the DPU compute bottlenecks, which cause mob tasks to stall. As a result, the observed host utilization appears lower, but this is due to underutilization rather than efficiency. DShuffle also significantly improves the utilization of disk and network resources. During the map phase, network and disk bandwidth utilization increased by 3 times and 2 times respectively, as shuffle logic is executed earlier and the intermediate results are persisted proactively. In the reduce phase, since data have already been transferred to the designation nodes over the network, the host only needs to perform sequential reads, resulting in higher disk bandwidth utilization. Next, we present the scalability evaluation results. By varying 2 key factors, dataset size and number of partitions, we demonstrate the scalability of DShuffle. As the dataset size increases, the performance gain from DShuffle offloading remains stable, with a slight improvement. This indicates that DShuffle scales well with increasing dataset size, and performs even better under larger datasets, as the shuffle pressure becomes more significant in such scenarios. As the number of partitions grows, the performance trend of the DShuffle system closely follows that of native Spark, further indicating good scalability. We also evaluate the performance of DShuffle under high concurrency workloads. In this test, we gradually increased the number of concurrently running foreground workloads, each running on a 6-core, 12 GB executor. We measure both the performance of DShuffle and the resource utilization of the DPU. The results are shown in the figure. As observed, DShuffle demonstrates good scalability as the number of concurrent workloads increases. Even with 8 executors, DShuffle continues to deliver performance improvement. At this point, both host CPU and the DPU resources are full utilized. Finally, we present us with a summary. In this presentation, we show that shuffle operations impose significant CPU overhead due to serialization, garbage collection, and file I/O. And existing optimization approaches fail to fully eliminate the shuffle overhead. To fundamentally address the shuffle overhead, we propose DShuffle, an efficient offloading framework tailored for shuffle operations. By leveraging techniques such as DPA-accelerated serialization, DPU direct building, and fine-grained pipeline shuffle, we achieve full offloading of shuffle operations while also deliver significant performance improvements. Our evaluation on real Bloomfield 3 hardware shows that DShuffle can significantly reduce the CPU overhead and improve system performance. Thanks for your attending. I'm happy to take any questions.